Hi friends, you would have studied that in a power system many generators and many loads are connected through transmission lines. So let's consider a power system where 3 generators and 2 loads are connected. And it is also possible that a load may take electricity from more than one generator. It is not necessary that a load will take electricity from one generator only, and it is also not necessary that a generator will supply electricity to only one load. A generator may supply many loads, and a load can take electricity from many generators. Like in this diagram, here is we have load 1, so it may take current from generator 1 also, generator 2 also. In some situation it may take electricity from all 3 generators. Okay, so let's say it is taking electricity from generator 1 and generator 2, and let's say load 2 is taking electricity from generator 3. So this load will take current from generator 3 and generator 2. Okay, and these are connected through transmission line. Let's say this is a transmission line, this is also a transmission line. Suppose load 1 is connected near generator 1 only. Okay, so here no need of transmission line. So if you will see the current in the transmission line, there will be some amount of current in this transmission line, some amount of current in this transmission line, depends upon which loads take what amount of power from which generator. But if you will consider this junction, there is large amount of flow of current through this junction. Okay. So whenever in power system uh, there is a point from where a large number of current flows or large number of current comes, at that point we need metallic bar or bus bar. A bus bar is used to conduct large amount of current through it. So whenever a junction, there will be a junction, from that junction a large amount of current will flow, and at that junction we need bus bar. So instead of showing it, now as I said earlier, a generator may supply many loads. So if it will supply many loads, okay, it may be connected to many loads or many generators. Okay, so there will be from the generator terminal many lines will go, so there will be a junction. So instead of at this point we need a bus bar. So instead of showing a junction, we will connect a bus bar. So now to this diagram I will make like it. Generator 1, and for generator 1 there will be a bus bar, then it will supply a load, then it will be connected to generator 2. This will be bus of generator 2, then generator 3, bus bar of generator 3, and at this terminal near generator 3 we have a load. Even a load may be connected to many generators. Like this is a load, it may take current from other generators also. You may take current from other generator also. Let's say we have a generator here. So instead of this point we will connect a bus here, and we will show like this. Okay, so we will say in power system there are many buses. The bus may be generator bus, load bus, and slack bus. We will study in load flows types of generator. Okay. So many buses are connected in a power system, and corresponding to voltage of this generator, there will be some voltage of this bus. Similarly, voltage of this bus, and there will be some amount of current flowing through the bus, and there will be some voltage. And there will be some relationship between voltage of a bus and current of a bus. In fact, the voltage of a bus does not depend upon the, in general, voltage of any bus, it will not only depend upon current flowing through this bus only. In general, voltage at any bus, let's say this bus, it will depend upon the current flowing through this bus, current flowing through this bus. Okay, it will in general depend upon the all currents, or current at any bus, this current, it will depend upon voltages of all the bus in general. Okay, let's say we have 4 buses here. There will be some voltage of this bus, and what will be current of this bus? If I show a junction, 2 currents are coming, I1, I2, and let's say I3 and I4. I will write I1 plus I2 equal to I3 plus I4. So what will be the current through junction? The total incoming current or the total outgoing current. These two will be equals. So whether I say total incoming current on a bus or total outgoing current through a bus, this will be same. So we will define current of a bus is total outgoing current through a bus. This will be current of bus. So this current through any bus, let's say this is bus 1, so I will define it with I1. So I1 will depend V1 voltage of bus, V2 voltage of bus 3, V3 and V4. In general, this will be function of all the bus voltages, because in this line what amount of current is flowing, it will depend upon V1 and V2, and this current constitute in the current of bus 1. So this current depends upon V1 and V2, so the current of bus 1 will also depend upon V1 and V2. Similarly, current flowing in this line, it will depend upon V1 and V3. Okay. So in general we will say all the currents are, this current is function of all the voltages V1, V2. Similarly, current at bus 2, this will be function of, obviously it will be a linear function of voltages. This will be function of all the voltages. And similarly we can write this type of relation for voltages. Voltage at each bus will depend current through all the buses. It may depend like I1, you may have this kind of equation, K1 V1 plus K2 V2 plus K3 V3 plus K4 V4, a linear function, and the unit of K1 K2 will be admittances. Similarly, we may have I2 equal to some other constants into V1, V2, V3 and V4, and this will be the unit of K1 K2 will be admittance. So this way we can construct a matrix I1, I2, let's say there are 3 buses, and here all the voltages on which all the current depends. I1 will be K1 V1, then K2 V2, K3 V3. Similarly, there will be some constants here, which will show the relationship between I2 and V1, V2 and V3. And unit of all these constant will be admittance. So this will be called admittance matrix. Admittance matrix, and this may also be called as Y-bus matrix. And similarly, if you will take V1, V2, V3 can also be represented as a function of I1, I2, I3. V1, V2, V3, sorry, I1, I2, I3. Okay. And here you may have constants. The unit of that constants, those constants will be impedance. So better to write Z11, Z12, Z13. Similarly, there will be some constants for V2. So this matrix will be called impedance matrix, okay, or Z-bus matrix. And Y-bus matrix and Z-bus matrix will be inverse of each other. If you will multiply inverse of this matrix both sides, in the right hand side you will get V1, V2, V3 in terms of I1, I2, I3. So inverse of this matrix will be Z matrix. Okay. So now I will take a 3-bus system, and in 3-bus system, knowing the values of impedance or admittance of transmission line, we will try to construct Y-bus matrix, which will show the relationship between all the bus currents and all the bus voltages. Let's say this is bus 1, this is bus 2 and bus 3, and here is the transmission line which connects bus 1 and bus 2. Similarly, this transmission line connects 1, 3 and 2, 3. So buses are connected to each other, and there will be some impedance of transmission line. Some resistance may also be there, so better to write, although reactance dominates, but better to write it is Z1. And if impedance of transmission line is given, if Z1 is given, so what will be admittance? Y, this will be 1 upon Z1. So if Z1 is given, you can write it in the form of 1 upon Z1 will give you admittance. So let us represent it with Y admittance. And this is admittance of which transmission line? This is the line which connects bus 1 and bus 2. So I will represent it as Y12. And this is what type of transmission line I have taken? I have represented transmission line with only an impedance. So this is modeling of short transmission line. Short transmission line. In case of medium transmission line, we would have to take capacitances also. So that depends upon the which type of modeling we are using for medium transmission line. We may have pi model or T model, so that we will discuss later. First discuss for short transmission line. Similarly, here we will have admittance, and the name of this admittance will be Y13 because it connects bus 1 and 3. And here we will have Y23, or this can also be said Y21. Y21 and Y12 is same. So apart from these admittances, it's not necessary that some buses they also have shunt elements. Okay. For voltage control, we connect a capacitor. We connect a shunt capacitor for voltage control to boost the voltage. Or to avoid for anti-effect, what we do, we connect a shunt inductor. Shunt inductor means from bus you will connect an inductor and you will connect the other terminal of conductor to ground. So to boost the voltage we may have capacitor here, or to avoid the Faraday effect we may have shunt inductor here. So in general the shunt element may be inductor or capacitor. Suppose if it is a capacitor, obviously its admittance will be, its impedance is XC is, this is always minus 1 upon j omega. No, it is 1 upon, let's say this is 1 upon j omega c. This is impedance of a capacitor. What will be admittance? Admittance of a capacitor, if you will take inverse of it, you will get j omega c, and omega c is positive, so here you will get j positive quantity, the admittance of a capacitor. Similarly, if you want to get the admittance of an inductor, first find out the impedance. Impedance is j omega l. Okay. Now to find out admittance of an inductor, you will take inverse of j omega c. So this will be 1 upon, this is j omega l, this will be 1 upon j omega l. Now when j will come in numerator, it will become minus j. So admittance of an inductor is minus j 1 upon l. This is a positive quantity. So overall you will get a quantity which will be written, which will be negative of j, and here will be some magnitude. So in capacitive admittance you will have j positive quantity, in inductive, in admittance of inductor you will have negative j quantity. So when two buses are connected through transmission line, in transmission line you will have reactance dominates, and the admittance of reactance will be minus j some quantity, some magnitude. So normally you will have a negative admittance here. Here also negative admittance, here negative admittance, and normally buses are connected with shunt capacitor. So the admittance of capacitor is positive, so you will have a positive quantity here. Okay. So let's say this is shunt element of bus 1 and its admittance is y11. Here we have, this is y33 and this is y. The voltages will be, bus 1 voltage is V1, bus 2 voltage is V2, and bus 3 voltage is V3. Now let us define current of each buses. What will be I1? Total current that is flowing through the bus. This current, what is total current of bus or current of a bus? Total incoming current or the total outgoing current. So we will take a reference showing that a current is going away from bus. This is going away from bus, this is also going away from bus, and this is going away from bus. So I1 will be summation of these three currents. Similarly, here also we have to take a reference which indicates the current is flowing out of a bus. This current plus this current plus this current, this will be current I2, and similarly I3. Now what will be I1? If voltages at two buses are known and the admittance is known, what will be current in terms of voltage? Voltage is nothing but I into impedance. So I will be 1 upon impedance into voltage, and 1 upon impedance is admittance. So I is admittance into voltage or voltage difference. Okay. So if the reference is taken for bus 1, reference of current is taken left to right. Okay. So this current will be, if reference is taken from bus 1 to bus 2, the voltage difference will be V1 minus V2. I1 will be Y12 into V1 minus V2. Similarly, what will be this current? V1 minus 0 into Y11. Y11 into V1 plus, what will be this current? Y13 into V1 minus V3. Okay. So in the expression of I1 we have V1, V2 and V3. Similarly, what will be I2? Y22 into V2 minus 0. Y22 into V2 minus 0. This current, what is this current? Y12 or Y21 into V2 minus V1, because for this current I am taking reference from right to left. So for this current the voltage difference will be V2 minus V1. And Y23, the third current, V2 minus V3 into Y23. Similarly, I3 will be Y31. This is Y31. Whether I write is Y13 or Y31. For I3, I will name it as Y31. Y31 into V3 minus V1 plus Y32 into V3 minus V2 plus Y33 into V3. Okay, now we will write I1 will be, what is the dependence on V1? Here you have V1, V1, V1. So take all the terms together involving V1. This will be Y11 plus Y12 plus Y13 into V1 minus Y12 into V2 minus Y13 into V3. Similarly, I2 will be first write dependence of V1. So this will be minus Y21 into V1 plus Y22 into V2 plus Y23 into V2 plus Y21 into V2. So here you will have Y21 plus Y22 plus Y23 into V2 minus Y23 into V3, and I3 will be minus Y31 into V1 minus Y32 into V2 plus Y31 plus Y32 plus Y33 into V3. Now when we will represent I1, I2 and I3 in matrix form, V1, V2, V3, and here we will have a quantity which will have unit of admittance. So dependence of V1 and I1 and V1 will be represented here, and we will represent it as, here you have 1, here you have 1, Y11. Similarly, here we will have Y12 and here Y13. This one represent current, and the later quantity 1, 2, 3 represent for voltage. For I2, so here we will have Y2 and 1. It means I2 will be Y21 into V1, Y22, Y23, Y31, Y32 and Y33. T3. Okay, so I1 equal to Y11 into V1. Now compare in the relation of I1 and V1, what is constant? Y11 plus Y12 plus Y13. So capital Y11 will be small y11 plus a small y12 plus a small y13. And what is a small y? A small y represents various admittances. If it is 1 1, then it is shunt admittance of bus 1. This is admittance of transmission line connecting bus 1 and bus 2. Okay. What will be capital Y12? Capital Y12 is relationship between I1 and V2. I1 and V2. Okay, when you will multiply it, you will write y11 v1 plus y12 v2. So plus y12 v2 is minus a small y12 v2. So capital Y12 will be minus of a small y12. Similarly, capital Y13 will be minus of a small y13. Y22 is, then comes Y21. Y21 will be minus of y. Now you can compare it in the second equation. Minus of y21, which is nothing but y12. Y21 is equal to y12. Y22 will be y21 plus y22 plus small y23, and capital Y23 will be minus of y23. Y31 is minus of a small y31. Y32 is minus of a small y32, and capital Y33 is y31 plus y32 plus y33. If you observe, all the diagonal elements are, what is diagonal element? Capital Y11, this admittance plus this admittance plus this admittance. All the admittances connected, anyhow all the admittances which are connected to bus 1. What is y? Capital Y22, Y21, this admittance plus its shunt admittance plus this admittances. So all the diagonal elements will be nothing but summation of all the admittances which somehow connected to that bus, either through transmission line or through shunt. And what is non-diagonal elements? Non-diagonal elements are nothing but it is just negative of the admittances y. Let's say this is capital Y12, so this will be minus Y12. Let's say this is J2 and J2.5. This is bus 1, 2 and 3. Okay, and bus 3 has, or let's say bus 2 has a shunt capacitor, and it is given as minus of J2, and you are required to find out admittance matrix for this bus. So first you will have to find out small y11, small y12, small y13. Then this is for I1, and for I2 you need a small y21, which is nothing but a small y12. Then you need y22, y23. Y23 is also equal to, okay, I will write later. This is for I1, this is for I2, and for I3 the constant quantities are y31, which is also equal to y13. This is y32, which is equal to y23, and y33, which is nothing but shunt element, the admittance of shunt element connected at bus 3. So what is y11? Here you have an inductor, and this is a positive quantity. So whether it will be impedance or admittance, in inductor this is j omega L. The impedance is j omega L. So impedance will be always positive j and some magnitude. Okay. So if it is positive j, the quantity is positive j. So this is obvious that it is its impedance. So this cannot be y12. Okay. In y12 we have to take admittance, and here it is impedance. So we need to convert it. If impedance or the reactance is J2, so what will be admittance? 1 by J2. So y12 will be minus J 0.5. There is no shunt element connected. Okay, you can consider it as open circuited. If it is open circuited, so impedance will be infinite, then admittance will be 0. So y11 is 0. y13, 1 and 3. Inductor is shown here and it is J2. So this will be impedance, and you have to take reverse of it. So reverse of 1 by J2 will be minus J 0.5. Okay, if it was given like, if a capacitance was given here, okay, I will do it here. Next, y21 is equal to y12, so this will be minus J 0.5. y22 is shunt element of the admittance of shunt element. So here we are given with minus J2. So what will be this? An impedance or admittance? For a capacitor, the impedance is minus 1 by j omega. No, impedance is 1 by j omega. And this will be minus j, impedance is 1 by j omega c. This will be minus j 1 by omega c. This is nothing but impedance of capacitor. So for capacitor, impedance will be minus j quantity. So if minus j is given, this will be impedance, and y22 is admittance. So you need to take inverse of it. Okay. So inverse of 1 by minus j2 will be j 0.5. Here the notation, whether it is capacitor or inductor, this is also important. Whether you have notation of inductor or capacitor, this is also important. And here whether it is given as plus j or minus j, it is also important. Let's say you are given with minus j2 only, and you are given with an inductor. So what will happen for inductor? I just changed capacitor to inductor. I maintained it constant. I did not change it. Now what will happen? What will be the value of y22? Inductor is given as minus sign. Okay. If it was impedance, then impedance of inductor would be plus j. It cannot be impedance, this will be admittance only. So in that case y22 would be minus J2 only. You don't need to take inverse of it, because inductor is given as minus, it is given in form of minus J. So this has to be admittance only. Okay, what will be y23? y23. Okay. Here you are given with inductor with positive J. So this will be impedance. You need to take inverse of it. This will be inverse of 1 by inverse of J 2.5 will be minus J 0.4. y31 is nothing but y13 is minus J 0.5. y32 equal to y23, this is minus J 0.4, and y33 is admittance of shunt element at bus 3. This will be 0. Now we can form the matrix. Here we have y11 is nothing but the summation of all the admittances connected to bus 1. So y11 plus y12 plus y13, this will be minus J. Now what will be y12? y12 is negative of small y12, negative of this quantity. This will be J 0.5. y13 is J 0. Similarly for I2, the diagonal element will be summation of all these three elements. Y22 is summation of all the admittances connected to bus 2. So this will be minus J 0.5, J 0.5 minus J 0.4. So we will have minus J 0.4. And in the third diagonal element you will have minus J 0.9. And in off diagonal element this is y12, and here you have y21. So y12 and y21 are same. This is J 0.5. Here you have to write y23. So y23 is minus J 0.4. The small y23 is minus J 0.4. But here you have to represent capital Y23. So capital Y23 is minus of Y23. So if you will take minus of this quantity, you will get positive J 0.4. Here you have Y31. Okay, and Y31 is equal to Y31 will be equal to Y13. Capital Y13 is J 0.5. This is J 0.5. And here you have Y3 capital Y32, which is nothing but capital Y23. This is minus of Y23. So minus of Y23 is plus J 0.4. Okay. These two quantity will be same. These two quantity will be same, and this quantity and this quantity will be same. This will always happen in Y bus matrix. And the diagonal elements are summation of all the admittances. If you will take J common, normally in question J will be taken common. So here you will have minus 1, 0.5, 0.5, 0.5, minus 0.4, 0.4, 0.5, 0.4, and minus 0.9. Here you have four quantities equal, but in general, because I have taken impedance of two buses two lines equal, so that's why you are getting four quantities equal, but in general these two quantity will be equal, and this 0.5 is equal to this 0.5. Okay, so now if you are given with a Y bus matrix of a power system, let's say you are given with this power system, and if you are asked to find out what is the impedance of the line which is connected between bus 2 and 3. Suppose you are given with this admittance matrix and you are required to find out impedance of the line between bus 2 and bus 3. So what will be impedance? Impedance will be inverse of admittance, and admittance is small y23, not capital Y23, and a small y23 is 1 by minus of capital Y23. So what you will do, here you have y23, this will be 1 upon minus of j 0.4, which is nothing but j 2.5. So impedance is equal to j 0.5, or inductor will have a reactance of 0. If I said 0.5, this is 2.5. So the line which is connecting between bus 2 and bus 3, this will have a reactance of 2.5 ohm. What will happen if we will add all the elements of a row? If you add all these three elements, what you will get? You will get 0 here. Okay? If you will add all these three, here you will get j 0.5, and here you will again get 0 here. So what was the shunt element connected at bus 1? This was 0. The shunt element connected at bus 2 is, this is minus j2, and here what it will give you, you are adding three admittances. So you are adding here, this is an admittance, okay, and here the admittance of, this was a capacitor originally, admittance of this capacitor is j 0.5, and in the third row you are getting 0 because there is no shunt element connected. So addition of all the elements of any row, let's say first row, this will give you the admittance of the admittance of the shunt element connected at bus 1. If you will add all the elements of row 2, this will give you the admittance of shunt element connected at bus 2. You can verify it here. If you will add y11, y12 and y3, what you will get? This is capital Y11, okay, and if you will add y12 here, what is y12? This is nothing but minus of y small y12 plus y13. I'm adding capital Y11 plus capital Y12 plus capital Y13. So here you will get minus of a small y13. So these two will be cancelled and you will get a small y11, which is nothing but, it shows the shunt element of bus 1. Similarly, if you will add this, you will get one addition. Here you will get y22 and here you will get y33. Okay, so this was the formula for admittance matrix, and this was for short transmission line. In the transmission line, I have shown only one impedance. Okay, so this was model of short transmission line. What will happen for medium transmission line? We talk about medium transmission line. Medium transmission line, there are two models. In one model, the two series, the total series impedance, it is divided into two parts and connected at the extreme end of the transmission line. Let's say this is one end, so this will be connected to the extreme end. There cannot be any shunt part here, and this is second, and the shunt part is connected in the middle. This is approximate model of medium transmission line, and this is called T model. We have already studied in the modeling of transmission line, where we have also calculated ABCD parameters. Okay. So if the total impedance of the transmission line is Z and total admittance is Y, this will be Y, and this is Z by 2, and this is also Z by 2. The total impedance is split into two parts and connected at the extreme end of the transmission line. So this is T model, and in the other model what is done, the total admittance is split into two parts and connected to extreme ends. Impedance is connected here, Z, and the total impedance Y is divided into two parts, so this will be Y by 2. Let us not represent with capacitor, let us represent with a box, or we may represent, if we neglect the loss, we may represent it with capacitor. This is end 1, this is end 2, this is pi model. And if you are given with any of these two models, you have complete information about the medium transmission line. If that medium transmission line given in T model, you can convert it into pi model and vice versa. And in both cases we have derived the ABCD parameter of the medium transmission line, and also for long transmission line. So even if ABCD parameter is given, you can find out the pi model of transmission line. So let's say now it is a medium transmission line. So in modeling of medium transmission line, what we will do, we will represent it in pi model. While finding out Y bus matrix, it is better to represent a medium transmission line in pi model. The reason is, in pi model, the total impedance will be connected here in the middle, or in the series. The total impedance will be connected here. This will be Z, and we will say Y12 is 1 upon Z. And the shunt part of the medium transmission line, this is connected to the extreme end. Means extreme end means you can say that, let me first write this will be Y by 2 admittance of transmission line, and here also this is also Y by 2. Okay, now if the admittance part of the transmission line, it is connected at the extreme end of the transmission line, it means what is the extreme end of this transmission line? This is connected to bus. So instead of connecting the admittance of transmission line to the transmission line, it is connected with the bus only, because these two points are same. So this will be connected as capital Y by 2, and this will be connected to bus 2 only, capital Y by 2. So now the shunt part of transmission line in this system, the shunt part of the transmission line is nothing but the shunt element for buses. In the first experiment you have bus 1, so in this part the shunt element of, or the shunt part of transmission line will become the shunt element connected to the bus 1. So the total shunt admittance at bus 1 will be its original shunt element Y11 plus capital Y by 2. This comes from the modeling of transmission line. Let us not write it Y11 dash at this time. This is original shunt element of bus 1, Y11. Similarly, here you may also have this transmission line is also medium. This is also medium transmission line. So in the modeling of this transmission line, we will again have a shunt element, and this shunt element will be connected at bus 3, and the half part will be connected at bus 2. Okay. Let's say this is first transmission line. So here you will have capital Y1 by 2, capital Y1 by 2. And let us say this is second transmission line. So this will be the shunt part of second transmission line, and here also shunt part of second transmission line. And let's say this is third transmission line. Here you will have the shunt part of the half of shunt part of third transmission line, and on the other extreme end also Y3 by 2. And in the pi model, here you will have impedance of transmission line 1, impedance of transmission line 2, and impedance of transmission line 3. So Y12 between bus 1 and bus 2, this bus 2, this will be 1 upon Z1. Y13, the admittance between bus 1 and bus 3, this is bus 3, this will be 1 upon Z2, and Y23 will be between bus 2 and bus 3 you have third transmission line. So there is nothing new in the off diagonal elements. Okay. So what is the effect of medium transmission line? The effect is that overall the shunt element connected to a bus, this will be changed. Now what will be mu Y11, its original shunt admittance, plus there will be one shunt element which will be due to first line and another shunt element due to second line. This will be capital Y1 by 2 plus capital Y2 by 2, where Y1 is shunt part of the admittance of shunt part of line 1, and similarly for Y2, what will be Y22 dash original shunt part plus here Y2 by 2 plus Y3 by 2, Y2 by 2 plus Y3 by 2, and Y3 dash will be Y33 plus Y3 by 2 plus Y1 by 2. What happens in medium transmission line? in the pi model of medium transmission line, the shunt element is, the series impedance is connected in the middle and the shunt part is connected in the extreme end. That's why we could reach on this conclusion. If the shunt part was not connected at the extreme end, let's say shunt part is connected here, so there would be some impedance here also, and in that case we could not say that the shunt part of line will act as the shunt part of bus. But in the modeling, this is connected at extreme end, and on the extreme end of the line you have bus. So you have the new shunt elements, so this way you can find out the new admittance matrix. Let's say we are given with a Y bus matrix of a 3-bus system, and these buses are connected with medium transmission line. Okay. We have bus admittance matrix given and buses are connected with medium transmission line, and it is also given that there are 3-bus system. These are connected with medium transmission line. Bus 1 has a shunt element which has reactance, it is given as minus J5, and bus 1 has no shunt element, bus 2 has no shunt element, bus 3 has no shunt element. Okay. And now you are required to find out the series and shunt parameter of the line. Okay. Let's say this is Y1, transmission line 1, this is transmission line 2, and this is transmission line 3. So we have to find out Z1 and Y1, the series parameter of line 1 and shunt parameter of line 1. Okay. Similarly for series parameter of line 2 and shunt parameter of line 2, Z3 and Y3. Okay. Bus 1 has a shunt element which is given, and bus 2 and bus 3 has no shunt element. It means these shunt elements are 0. Okay, we are given with Y11 is equal to, since this is minus for capacitor will show an impedance, so you will have to take inverse of it. This will be J0.2. Okay. Now to calculate the parameter of transmission line, we will use the bus admittance matrix. Now if you will add all these 3 elements, what you will get? The overall shunt parameter of bus 1. If you will add it, what you will get? 0.9, 0.6, you will get J0.6. And what is this? The overall shunt parameter of bus 1, and I represented it as Y11 dash. Similarly, what will be Y22 dash? Addition of these quantities, this will give you J0.5. Similarly, Y33 dash will be J0.4. And what is Y11 dash? The original shunt element of the admittance of original shunt element plus the shunt admittance due to transmission line. So at bus 1, this will be Y1/2 due to first transmission line, and due to second transmission line you will have Y2/2. So the overall Y11 dash will be Y1/2 plus Y2/2. Similarly, Y22 dash will be Y22 plus Come to second transmission line. This is connected through, coming to second bus. This is for second bus. And bus 2 is connected to first transmission line and third transmission line. This will be y1 by 2 plus y3 by 2. And similarly you will have, here you will have y33 plus 1 2 1 3. Now we will have 2 3, y2 by 2 plus y3 by 2. Now y11 is given as j2. This is j 0.2. Okay, so from here we will get y1 plus y2. If you will subtract, you will get j 0.4. y1 plus y2 will be y1 j 0.4 into 2, j 0.8. Similarly y1 plus y3 will be, y22 is 0, y33 is also 0. This will give you j1, and y2 plus y3, this will be j 0.8. If you will add all these three, you will get y1 plus y2 plus y3 as, you will get 2 into y1 plus y2 plus y3 as j 2.6. So this quantity will be j 1.3. Now subtract y1 plus y2 from this quantity, you will get y3. y3 will be j 0.5. Subtract this, you will get y2. y2 will be 1.3 minus 1, j 0.3, and y1 will be, subtract this, 1.3 minus 0.8, j 0.5. Okay, so we have shunt part of all the transmission line, and finding series part is very easy. If you want to find series part here, so this will be corresponding to capital Y12. You will find capital Y12 from matrix. Here you will have j 0.4. So y small y12, which is admittance of the line, this will be minus j 0.4, and z will be 1 by y12, this will be j 2.5. So the reactance of this line will be 2.5 ohm, and the admittance will be j 0.5. This is z1. Similarly z2 will be the series part of second transmission line, this part. So for this part we will use this bus 1, this is bus 3. We will use y13, and this is nothing but minus of capital Y13. Minus 1 divided by Y13 is j 0.5. You will get it 2j, and similarly you will get Z3 as j 1 by 0.6, j 1.66. So this was in the pi model of medium transmission line. Even if you are not given with the pi model, suppose you are given with the T model of medium transmission line, you will first convert it to pi model, and then you can use this procedure. And for long transmission line, suppose you are given with a long transmission line is given, long transmission line. So even for long transmission line, you can find out ABCD parameter. If it is given in the form of ABCD parameter, and we have also studied in the modeling of transmission line that how can you get the approximated pi model of so if you are given with ABCD parameter, write ABCD parameter of long transmission line and then equate it with the ABCD parameter of medium transmission line. Okay, this will be something like 1 plus yz by 2, and d is also 1 plus yz by 2. This is formula for ABCD parameter of medium transmission line, and in the left hand side you will have ABCD parameter of long transmission line. So approximately you will equate it and you will get y and z of the medium transmission line. So again you will have a pi model of medium transmission line and you will use the same procedure.